Hello, welcome to another module in this massive open online course on principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous modules we have characterized the performance of a wireless communication system, and we have noticed that the bit error rate performance of a wireless communication system is very poor. In particular, the bit error rate of a wireless communication system decreases only as 1 over SNR. Right, while the bit error rate in a wireline system decreases exponentially e to the power of minus half SNR, the bit error rate of a wireline communication system decreases only as 1 over SNR. And therefore, what we want to do in today's module is we want to intuitively understand the reason behind this poor performance of the wireless communication system. So, what we want to do today is we would like to basically understand perform an analysis or intuitively understand the reason behind this poor performance of the wireless communication system, and we will notice that the reason that this poor performance arises is because of the deep fade events, because of the deep fade nature of the wireless communication channel. So, what we are going to do today is we are going to do a deep fade analysis. A deep fade analysis of wireless communication. In particular, we would like to understand why is the performance of a wireless communication system poor? Why is the performance of a wireless why is the performance of our wireless communication system poor, and this can be explained on the basis of the deep fade nature of the deep fade events in the wireless, in the fading nature of the wireless communication channel. So, this can be explained or can be explained based on the deep fade events in this can be explained on the basis of deep fade events. The key here is to realize the deep fade events in the which occur in the fading nature, in the fading process of the wireless channel. And just to remind you briefly about the concept of deep fade, we said that the wireless channel is a fading channel. We said that the wireless channel is fading in nature, correct, which means our wireless channel amplitude is varying, and at a certain point the wireless channel is there is a drastic, this is the fading nature of the wireless channel. So, if you look at this, this is my fading wireless channel, and there is a here at this point there is a drastic decrease in the strength, or there is a drastic dip in the strength or amplitude right. There is at some point there is a drastic dip in the strength or the amplitude of the wireless channel, and this is basically our deep fade, and when this occurs we call this our deep fade event. This is basically our deep fade event, right. And this, what we want to understand is what is the impact of this deep fade, how does this impact, or how does deep fade compact wireless communication. So, what we are saying is there is a fading nature of the wireless channel, and at certain points, at some instance, that amplitude or the received power or the gain of the wireless channel dips significantly, and when this significant dip occurs, we call that a deep fade event. And what we would like to understand is precisely how does this deep fade event, or how do such deep fade events, or what is the impact of these deep fade events on the performance of the wireless communication system. And we are going to see that these deep fade events, they have a very significant and a profound impact on the performance of the wireless communication system. All right. So, what we would like to do is, first we would like to model the deep fade event. So, consider our fading wireless channel model. So, consider or fading channel model, which is basically given as y equals, I hope everyone remembers this is y equals h x plus n, where y is the received symbol, r x is the notation for the receiver, n is the Gaussian noise, in fact white Gaussian noise of variance or power sigma square. My h equals a e to the power of j phi is the fading coefficient or fading channel coefficient, and x is the transmitted, my x is the transmitted symbol, and therefore, the transmitted symbol has power. The power of the transmitted symbol is P. Therefore, we already said that the received power, therefore, received power equals, because remember the transmitted symbol x is multiplied by the fading channel coefficient h. Therefore, the transmit power P is multiplied by the square of the amplitude of the fading channel coefficient. Therefore, the received power is the transmit power P times magnitude h square, which is basically a square. So, that received power is equal to P transmitted power times magnitude of h square, which is basically P times a square, or which is equal to a square times P. And the noise power, we have already seen, the noise power equals sigma square. So, noise power equals sigma square. And when can we say this communication system is in a deep fade? The performance of the communication system is very poor when the received power is less than the noise power, because if the received signal is below the noise threshold, then obviously you cannot detect the signal, or you cannot differentiate the signal from the noise, right. So, the performance, so the system is in a deep fade if signal power is lower, than the noise threshold, which means that when my received power is less than the noise power, which is sigma square, which means to say that a square p is less than sigma square, and this basically corresponds to, this event corresponds to our deep fade. What is the meaning of deep fade? When do we say that the channel is in a deep fade? We say that the channel is in a deep fade if the channel strength dips so much that we are not able to receive any meaningful signal power. that is the received signal power is much lower than the noise threshold, therefore, I cannot distinguish the signal from the noise. So, in that scenario we say that the channel is in deep fade, which corresponds to the criterion that the received signal power A square p is less than the noise power, that is sigma square. So, this is our deep fade event, and now if I simplify this further, I have A square p less than sigma square, which implies A square less than sigma square by p, but remember sigma p over sigma square equals SNR. So, sigma square over p equals 1 over SNR. So, this implies A square is less than 1 over SNR, or A is less than 1 over square root of SNR. So, my deep fade criteria, so fading coefficient is so poor that A is less than 1 over square root of SNR. So, when the fading coefficient A, amplitude of the fading coefficient A is less than 1 over square root of SNR, the received signal power is less than the noise threshold, and therefore, we say that the channel is in a deep fade. So, our deep fade condition in terms of SNR, so deep fade occurs, our deep fade occurs when A is less than 1 over square root of SNR. So, this is basically our condition for the deep fade. And now, therefore, we can ask at this point, now therefore, one can naturally ask what is the probability of deep fade. So, we have identified the condition for a deep fade. Now, one can ask what is the associated probability of deep fade. What is the probability of this deep fade? Well, the probability of the deep fade, which I am denoting by P of df, this is the probability of deep fade. This is equal to the probability that A is less than 1 over square root of SNR. So, the probability of deep fade P df is the probability that A, the amplitude of the channel coefficient h, is less than square root of 1 over SNR. And let us now calculate what this probability is. So, P df, which is the probability of deep fade, equals the probability that A is less than 1 over square root of SNR, and this we already said, this is our probability of deep fade. Now, the probability that A is less than 1 over square root of SNR is the distribution of A, distribution of the random variable A integrated from 0 to 1 over square root of SNR. That is, if I want to find the probability that the fading channel coefficient A lies between 0 and 1 over square root of SNR, I have to integrate the distribution between the limits 0 to 1 over square root of SNR. And remember, our channel is a Rayleigh fading channel, therefore, f of A, the distribution is 2A e to the power of minus A square. Therefore, the probability is given by the integral between the limits 0 to 1 over square root of SNR to A e to the power of minus A square dA, where this is our Rayleigh fading density. This is our Rayleigh density, and now you can see this integral 2A e to the power of minus A square equals minus E of minus A square evaluated by between the limits 0 to 1 over square root of SNR, which is basically equal to 1 minus e raised to minus 1 over SNR. So, this is basically equal to, so the probability of deep fade PDF equals, so the probability of a deep fade, the probability that the deep fade occurs equals 1 minus e raised to minus 1 over SNR. Now, this is the exact expression, however, we can simplify it further at high SNR using the following property. If x is approximately equal to 0, that is if x is close to 0, then we have e to the power of minus x equals or is approximately can be approximated as 1 minus x, e to the power of minus x is approximately 1 minus x. Therefore, my probability of deep fade is approximately 1 minus 1 over SNR at high SNR, because you can see from this expression when SNR is high, 1 over SNR is very small, and we are using the relation 1 minus e power minus x, we are using the relation e power minus x is approximately equal to 1 minus x when x is very small, and therefore, I have 1 minus e raised to minus 1 over SNR is approximately equal to 1 minus 1 over SNR, which can now be simplified as the 1's cancel, which can now be simplified as 1 over SNR, and this is really the key. Now, if you can look at this, what you can see is very interestingly, the probability of deep fade is equal to 1 over SNR, is approximately equal to 1 over at high SNR, the probability of deep fade is approximately equal to 1 over SNR. This is this quantity here, this is my probability of deep fade. This is my probability of deep fade at high SNR, which is proportional to 1 over SNR. And then what you can see is from the previous result, you can see that the bit error rate is proportional to 1 over twice SNR, or basically proportional to 1 over SNR, but 1 over SNR is the probability of deep fade. Therefore, what we can see here is essentially that my bit error rate, which is equal to 1 over twice SNR, is basically proportional to 1 over SNR, which is equal to the probability of deep fade, and that is essentially the most important result, which basically tells us that the bit error rate of a wireless communication system is proportional to PDF, where PDF is the probability of the deep fade, and this is the key result, because the probability what you are seeing is the bit error rate is proportional to the probability of deep fade, that is the bit error rate is proportional to probability of deep fade, and this basically captures the property of the important property that the bit error rate, the bit error rate is proportional to the probability of deep fade, and the high bit error rate that you observe in the wireless communication system arises due to the deep fade, due to the frequently occurring, due to the deep fade events in the fading nature of the wireless channel. So, the poor performance of the wireless communication system, so the poor performance of wireless channel arises from the deep fade. And in turn, we have said that deep fade events occur because of the strong destructive interference. When these multiple signal copies from this multipath propagation environment interfere with each other and they cancel, that results in a deep fade, the strong destructive interference. So, we have already said the destructive interference gives rise to the destructive interference in the wireless communication system, or the destructive interference of the wireless channel gives rise to the deep fade, and that is what significantly impacts the bit error rate. In fact, that results in a significant increase in the bit error rate of the wireless communication system, and that is the reason. So, the deep fade events have a profound impact on the performance of a wireless communication system, in that they significantly degrade the performance of the wireless communication system. And therefore, now we have to understand what are the techniques, how can we combat this fading, or how can we overcome this disastrous effect of this fading or this deep fade events in the wireless communication channel or the wireless communication system to improve the performance of the wireless communication system. So, what we are going to look at now is we would like to improve performance by basically avoiding deep fades or reducing the frequency that is avoiding deep fades or overcoming the deep fades, or overcome the effect of these deep fade events. And how do we do that? This is possible through the principle of diversity. So, what we would like to do is we would like to understand how to overcome this the degrading effect of this poor bit error, the degrading effect of these deep fade events, and the answer to that, the key to that lies in this concept called diversity. That is, diversity is the important principle or is the important property that we will use to overcome the impact of fading and thereby improve the performance of the wireless communication system. All right. So, let us stop this module here, and we will talk more about the properties of diversity or more about this principle of diversity in the subsequent modules. Thank you very much.